Okay, this is a continuation of 14.3. We were about to compute the second order partial derivative with respect to y, which again we do by the product rule. We take first the derivative of this first piece with respect to y. We get 6y, and then we leave the second part alone, x squared y plus y cubed with the cosine, and then plus we keep the first function as is and take the derivative of the cosine portion. We get negative sine x squared y plus y cubed, and then times the partial derivative of the inside with respect to y. We get x squared plus 3y squared, and so finally we have 6y cosine of x squared y plus y cubed minus x squared plus 3y squared squared times sine of x squared y plus y cubed. Okay, so that is the second partial derivative of f with respect to y. And so this is, there's lots of computations you can do. You know, let's just do maybe one quick computation before I want to do a little bit of geometric interpretation of these derivatives. So let's take the ln of x over y, and let's just compute the first order partial derivatives here. So we want to compute fx, which is partial f partial x. Well, what is this? This is going to be 1 over x over y times the partial of the inside with respect to x. And so we get y over x times, and the partial here, 1 over y is a constant, so effectively it's 1 over y times the partial of x of x, and so we get y over x times 1 over y times 1, and the y's cancel to just give you the 1 over x. Okay, so this is the partial of f with respect to x. On the other hand, if you take the partial with respect to y, this is 1 over x over y times the partial of the inside with respect to y. So this is y over x times, here x is a constant, so x times the partial of y to the minus 1. So we get y over x times negative y to the minus 2. So overall, well, these x's cancel. We have negative y times 1 over y squared. We get negative 1 divided by y. Okay, so you can get as crazy as you want with these derivatives, but they all basically follow the pattern of the usual derivatives viewing the other variable as a constant. So let's stop there with the computations. Let's do something where we can actually see what's happening. Let's take f of x, y to be 8 minus x squared minus y squared. And let's take the point P to be 0, 2, so that we want to compute del f del x at 0, 2, and del f del y at 0, 2. And so that we can actually draw this, because this is just an upside down paraboloid. The partials are very easy to compute. The partial with respect to x is negative 2x. The partial with respect to y is negative 2y. And at these points then, the partial with respect to x is 0, because you plug in 0. So this is, well, let me write it in detail. This is equal to negative 2 times 0, which is 0, and this is negative 2 times 2, which is negative 4. So let's draw the picture of this and see what's actually happening. So here is our coordinate plane, and here's 8 somewhere, and we have this paraboloid like so. And so what's happening? Well, we have a point here, somewhere here. This is the point 0, 2, and 4. 0, 2, 4. Now, along the, if you fix the x value of 0, so x here is fixed at 0. Let's say you fix x. So if you fix x equals 0, and we look at the zy plane, the z, so here's z, here's y. If you fix x equals 0, then you have this downward parabola. And now you're looking at the point in this when y is 2, so this is the point, well, let me keep the x coordinate there, where x is 0, 2, and 4. And if you take the derivative here, or if you take the tangent line will look something like this. This is the tangent line. The slope of this tangent line is -4. That's what we computed, right? We got -4 right here. So the partial derivative with respect to y is the slope of the tangent line when you fix the other variable and you get a particular curve. So this is the resulting curve. So this curve, this upside down parabola, which I'm just redrawing in red, if you take the equation of the tangent line, or you take the tangent line and you compute the slope, that's exactly the partial derivative which we computed. In this case, you're going essentially downhill with a slope of -4. In a similar way, if you fix y equals 2, what do you get? You get z equals 8 minus x squared minus 4, which is 4 minus x squared. And we're looking now at the point where x is 0, y is 2, and z is 4. Well, in the zy plane, so let me draw this now in the zx plane. So we're in the plane y equals 2, essentially, or I should say parallel to the zx plane. So here's z, I'll call it prime, because technically it's not exactly the z-axis, right? It's parallel to the z-axis. I'll call this x prime, parallel to the x-axis. Our parabola will be also a downward pointing parabola. But here now we're at the top of the parabola, 0, 2. So the tangent line here is horizontal. The slope is 0, and that's exactly the partial of f with respect to x at this particular point. So essentially, these partial derivatives are slopes of tangent lines. And let me try to draw, I'll attempt to draw both of these simultaneously in the three-dimensional space. I apologize if it's not the best drawing in the world. There are probably better drawings in the book. So here is your paraboloid, and here is your point. So this tangent line is m equals -4, and the other one, let me just change the color here to a different color. The other tangent line, I'll draw in blue, is this one. This is m equals 0, and that's essentially, if you look at the curve, let me draw that curve in yet another color here. Let's try gold. So here is this gold curve is the curve when you fix, this is when you fix y equal to 2. And tangent to that is this blue line. Okay. All right, so I hope you see what's going on here. There's this plane, which is fixing y equals 2, and then there's tangent to that, which is the blue line. Then there's the white line. This white curve, the white is essentially when you fix x equals 0, and tangent to that is the red line. Okay, so these are tangent lines, and so if you took, and we'll see this in the next section, if you take these two lines, so if you take the blue line and the red line together, remember they have a point in common. There is a point in common, which is of course the base point 0 to 4, and the plane that contains that is right here, which I'll draw and sort of shade in blue and red. So here's this thing is called a tangent plane. So there is a unique plane. I'll just state this. So this is essentially what we're going to talk about in 14.4. There is what's called a tangent plane to the surface at each point. In this case, we looked at the point 0 to 4, and this tangent plane is essentially the unique plane. It is a unique plane containing the tangential lines in the x and y direction. Okay, so I hope that was clear. So again, there's the tangent line in the x direction, the tangent line in the y direction, and together that'll form the tangent plane. What is the equation of that plane? That's what we're going to consider in the next section. So I will conclude it here. We'll start 14.4.